Hey everybody, Mr. Qualls again. We're going to talk about square roots and cube roots and what squares and cubes are and that kind of stuff. Okay, let's see. I've got a little extra shadow, so let's see if I can't. Let's see if I can't get rid of that light, and then we'll keep going here. Okay. All right, hopefully that looks a little better. So I'm going to talk about square roots today, and then these other things. I'll get to these other things. Eventually, what happens with certain pieces of math and certain problems that we have, we end up relating things to squares because squares and right triangles solve problems for us. And a case in particular that we do, where squares solve problems for us is when we're trying to find how far 2 points are from each other. And this is a lesson that I'm going to show you in a couple of weeks. And we want to know what that distance is. Well, we don't really have a diagonal measuring system, but we do have a measuring system that is vertical and horizontal. So the way that we get around this is not being able to find this is we look at this distance, and we're going to call that A, and we're going to call this distance B, and then we're going to call this distance over here C. And it turns out that if, and I'll have things where we'll prove these things, if we actually square this side, okay? So this length over here is A. And if we square the side, meaning that we multiply A times A times A is a rectangle, or can be represented as a rectangle. And if it is represented as a rectangle, A times A is a square because the side lengths are the same. So this square over here, and then this square on this side, if we create a square over here, it turns out that if we add A squared and B squared, A squared is a square, it's two-dimensional, and there's a 2 right there, and it's a square. B squared, it's two-dimensional, and there's a 2 there because then that's why we call it B squared, is because it's actually a square. A squared plus B squared actually ends up being the same size as C squared. Now that's not drawn to scale or perfectly, but it looks pretty good on the camera. But A squared plus B squared equals C squared. And then if we have A squared plus B squared equals C squared, what we want to be able to do is, if these were numbers instead, if this was 3 and this was 4, and we wanted to know how far C was, this ends up being 3 times 3, which is 9, because 3 squared is 9. And this ends up over here, if this is 4 squared is 16. Well, 9 plus 16 equals C squared. And if we take that idea, 9 plus 16, these two are 25 together. So that means 25 equals C squared. And then the length of this side over here, if C squared is this side times that side, something times itself made C squared. And if C squared is something times itself, it is C times C, which means that C must equal 5. So if I find the square root, if I put a radical over this and find the square root of C squared, and I find the square root of 25, I'm saying that C is 5. And that makes this length 5. It's a 3, 4, 5 triangle. Every time you see a 3, 4, 5 triangle, it's a right triangle because it's true for the Pythagorean theorem. And we're going to talk about that in a couple of weeks. But this is one of the reasons why we need to be able to find the square root of any number. Okay? Now, there are some that we can't find the square root to, but I'll get to that as well. So, but this is one of the most powerful problems solving tools that humans have is the Pythagorean theorem. And it's based on the idea that if we have a right triangle and we build squares on that right triangle, we know how the squares are related to each other, and through that we can find the square root. Okay, so basically a square root is a situation where we have maybe the number 81 and we want to know what the square root of 81 is. Okay, this is just a fancy, this is called a radical, and the number inside is called a radicand. And so what we're looking at here is we're looking at a number times itself must equal 81. Well, it's got to be 9, that's right. So it's got to be 9. Now, is there another number that you could multiply by itself and still get a positive 81? That's right, it's a negative 9. So this is a positive 9 or a negative 9. And we usually list them like this. The square root of 81 equals plus or minus 9. Think about that. Positive 9 times positive 9 is 81. Negative 9 times negative 9 is also an 81. We cannot use a positive times a negative because that would be negative, and that is not what we started with. So this stuff and the things that these problems are built off, we should be recognizing these numbers as what I refer to as suspicious numbers, because only a mathematician would put numbers like this inside other problems. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on, all the way down to 12. 1, 2, 3, 4, 5, 6, 7. Yes, 12. So if I see the number 144, I'm thinking 12 times 12. So the square root of 144 is 12 or a negative 12. Square root of 100 would be 10 or negative 10. And this is the way that you say this. The square root of 64, the square root of 64 is plus or minus 8. Okay? So sometimes we get, for now anyway, we get a number inside the square root of 10. And woo, square root of 10. Most people would just say, well, it's 5, right? No, because 5 times 5 is not 10, it's 25. So what we're looking at is we're looking at a number. If I took 3 times 3, I would get 9. And 4 times 4, I would get 16. So we're looking at a number that is between 9 and 16. And I'm going to leave that for another lesson that's in a couple of days. All right? So we don't necessarily need a number in here that works like these. We can find the square root of any number we need to. And right now, what we do is we use a calculator for these. Okay? Okay. Now, what numbers can't you find a square root for? Well, how about this one? What's the square root of a negative 25? All right, some of you may have said 5. Nope, can't get a negative 5 with a 5 times 5. But so negative 5 times negative 5, we can't do that either. Because negative times negative is positive. You would have to have a positive and a negative to end up with a negative number through multiplication. Neither one of those numbers can be the same because they're opposites. Therefore, we cannot right now find the square root of this number. The square root of a negative number is imaginary. So when we're talking about real numbers, and which is real numbers or any numbers that you guys have ever put on the number line or that you could find on the number line, the imaginary numbers are like this. There isn't a number that you can use multiplying by itself and actually get this number. So basically what's going to happen later, and there are people that need to use this in their math, not calculus, but engineers, certain engineers need to use this, certain scientists. And what we do is we take this idea out of it for a little bit, and then we keep it out here, we keep it outside the problem, and then we wait till we have more square roots of a negative number, or I is what we call it for imaginary, and then we mess with the I until the I can be multiplied again, become real, and then once it's a real number again, we put it back into the system. So it's just like extra, like if you were spending money and you were getting change, and you would keep your pennies until you can make dollars out of them, and then we keep it in the problem. Okay, but that's what we're doing right now for square roots. So like on example 3 in the book, it wants to know the square root of 121? Well, the answer is plus or minus 11. Something times itself must be 121, and that's what it is. Now, some of you guys are not going to recognize, okay? There's other numbers here. There's 169, 196. There are quite a few. Well, actually, there's an infinite number of squares like this. Now, when we do have a number that comes up with an integer for a square root, like that 121, what we're saying is we have a square, and inside that square, there are 121 squares inside, and what we're looking for is the length of one of the sides, okay? So 121, we want to find the square root. Square root equals positive or negative 11. Now, in this case, I don't have a length of a negative 11 because there's no such thing as a negative length. Therefore, we're not going to use the negative piece, and this is referred to as the principal square root. So the principal square root is what I used before with the triangle and trying to figure out how long the hypotenuse of the triangle was. The square root of 25 is 5 and a negative 5, but negative 5 for a length of a triangle doesn't make any sense because I can't have something that's negative 5 units long, okay? So here's the idea of a principal square root, and the perfect square is the square that has an integer for a side length. Now, I know these aren't drawn to scale, but this is 1, and its side lengths would be 1 and 1. This is 4 squared, and its side lengths would be 2 and 2, because the square root of 4 is 2. The square root of 1 is 1. There are 9 pieces here, and that means that this side is 3 long and this side is 3 long, because the square root of 3 is 9. These are perfect squares, and the reason they're perfect squares is because they have integers for side lengths. Integers for side lengths. So let's make one up that has, oh no, this one has an area of 10. What is this side length and what is this side length? Well, they're the same because it's a square, and there's a 10 for an area. So what I need is the square root of 10. And the square root of 10 is not a whole number. In fact, let me do this real quick. I don't want to estimate this one for you guys. We're going to do 10. The square root of 10 is 3.16. Okay, 3 times 3 is 9. 4 times 4 is 16. So I know that the square root of 10 lies between the square root of 9 and the square root of 16. The square root of 9 is 3, the square root of 16 is 4. So the square root of 10 has to lie between 3 and 4, and it turns out to be 3.16. That is not an integer. This is not a perfect square. So in a sense, all squares are perfect because the lengths of their sides are the same and they're perfectly built, because by definition, they must be built that way. However, in a mathematics sense, perfect means that they have integers for side lengths. So later in algebra, next year in algebra, you're going to force things into situations that have integers for areas. And then you're going to be able to find, or excuse me, they have a perfect square, meaning that you're going to be able to come out with integers for answers. And that's why we look at that. That's why we're looking at this right now, is because it's going to be built on later. Now, if we have this idea of a square root, and we have a square, and the square root, let's make this 25 because it's easy to work with, okay? If this was 25 for an area, then my side length would be 5 and 5, okay? This is a perfect square. I would use my principal square root for my side length, and I found the square root because the square root of 25 is 5. That's how I found my side lengths, okay? Well, what if we needed a cube root? Well, a cube is something that is built as a cube. It's a cube. It's cubic. Let's see if I have anything cubic in the room. I don't see my Rubik's Cube, which really kind of bums me out. It must be upstairs somewhere, you know, because everybody plays with those things and they probably stole it from me or something. Anyway, if a cube has been built, what that means is that the length here and the length here and the depth of the thing as well are all the same. So if I had something that looked like this and I needed it to be cubic, oh, markers are getting in my wood. All right. If I can hold this thing together without dropping it, this is a cube. It is 2. That was awesome. I'm going to do this again. I have hundreds of these. Don't worry about it. Oh, yeah. So this thing is too tall, it's too wide, and it's too long. So it is a cube. It is cubic. And if it is too tall, too wide, and too long, what we know about it is that there's 4 down here on this side, and there's going to be 4 up on the top. Okay? Now, if we've got this like this, let's build this cube. If this cube looks like this, if it's built like this across, you can see there are 1, 2, 3, 4, 5, 6, 7, 8 cubes in there. So if there were 8 cubes inside this thing, and 8 is a cube, well, what I want is a special notation. So I'm going to put my radical over it, but then I'm going to put a 3 in here, telling you something times itself 3 times is that cube. And the answer is 2 times 2 times 2. So this has to be 2. Now, can it be a negative 2? Because in this one, it could be a positive or a negative 5. Here, could it be a negative 2? Well, a negative 2 times negative 2 is positive, times a negative 2 is a negative 8. The answer is no. So cube root, we can only come up with this. Okay, so other cube roots that we might have are, and cubes get big fast. They get great, they become great numbers faster, and there we go. So if we had a 3 by 3 by 3, which is just like a Rubik's Cube, how many pieces would be inside there? Well, 3 times 3 times 3 is 27. So the cube root, my little 3, of 27 is 3. Okay, so there are certain cube numbers that you should see and should recognize as being suspicious. 1 times 1 times 1 is 1. 2 cubed, cubed, 2 cubed, with a 3 up here, 3-dimensional, and it's a cube. We don't call them 2 squarey things. They're 2 cubed because it's a cube. That's why we call it cubed. And that's why we don't have any special names for the 4th or the 5th or any other exponent, because we can't show the 4th dimension like this. Okay? The 4th dimension is typically considered to be time or position. So 2 cubed is going to be 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. So these things get really big really fast. 10 cubed is 1,000. 1, 2, 3 zeros. 12 cubed, I mean, you can cube all of these things if you want, but these things get very large very quickly. And you should recognize these numbers as suspicious. So a lot of times when you guys walk up and you say, well, I got 64 for an answer, I'm thinking, well, 64 is not only a square, it's also a cube. So this is 4 times 4 times 4, and it's also 8 times 8. Did I do that right? 4 times 4 times 4? And it's also 8 times 8. For some reason, I'm kind of, yeah, oh well. I lost track of what I was thinking about there for a second. I had a lot of stuff on my mind. Anyway, if you see these numbers, you should be suspicious that something is going on. And what I would think is that somebody, namely a math teacher, was sitting around and put these numbers in here on purpose. Who uses the number 49 for anything? Nobody, except a math person that wants to know if you remember that 7 times 7 is 49. 121, that's awfully suspicious. It looks like 2 11s. It is. Okay. 27, it's 3 times 3 times 3. It's also 3 times 9, and 9 is 3 times 3, so it's 3 times 3 times 3. Okay. So when we're looking at these and we need to find our cube root, some of these things you need to keep in mind. And once you figure one out, I would put it on the side of my paper so that I could use it in another problem. Now, this is a perfect cube because it has integer lengths for sides, for edges. The edges are integer lengths. You can also find the cube root of 50, but there isn't an integer cubed that makes 50. Something times itself 3 times is going to be 50, and it's going to have to be between 3 cubed and 4 cubed because that's where 50 falls. Now, if you need to figure this out, what you need to do is use this button on your calculator. It's got a little cube up there and an X. You put the 50 in and you punch that button and it shows you what to do, or it actually gives you the number, okay? Couple of things, last things here about the homework. If you're doing the homework and come on. If you're doing the homework and you have some funny things like this, I know you guys don't know everything about this, but if you had a 4 over a 25 and you had to find the square root of 4 over 25, this is really the square root of 4 over the square root of 25. I think we're done. Find the square root of the thing on the top, square root of the thing on the bottom. If we have a cube root on the top and a cube root on the bottom that you need to find, such as the cube root of 8 over 125. Well, this is the cube root of 8 over the cube root of 125. The cube root of 8, well, better mark it, otherwise it's square roots. If you do not put a number up here, it is a square root, which means 2 numbers. If you put a 3 up here, it means that there's 3 numbers in this. The cube root of 8 is dos, and the cube root of 125 is 5, right? 2 over 5. Last thing. I've already gotten a couple of people asking me questions about this. And they're just like saying, I don't know how to do it. Well, it's 0.4 with a repeat over it. Now, ignore the boxes that are in the book. Every single time we've come up with, there's boxes here. What do I do with these boxes? The same answer. It's always the same answer. Ignore the boxes. Write it down yourself and solve the problem. The book is written very poorly when it comes to leading you through problems. So remember, this thing is really a rational number. It would be 4/10. It would be 4/10 if that repeater wasn't there. So what I'm going to do is I'm going to make the top worth a little more so I can get all these 4s back in this. All I'm going to do is make it 4/9. I'm going to take one from the bottom and make it 4/9. That's it. There's no big secret. There's no work to be shown. I want you to know that this is how this works, because the other process is complicated to the point that it's above what you guys know. All right. Typically what it's done is it's kept for people who want to teach the stuff, and we don't use it either. All right. So I'll see you guys tomorrow. Do what you can on the homework. If you can't do something on the homework, bring those questions to the session tomorrow. I'll see you at the meeting. This thing never shuts off when I think it's going to.